The idea of this webinar is to show a bit of some of machine learning techniques, but not these very complicated and the ones that we can never even understand or explain. The idea here is to talk about a very straightforward, no photo. You want to see my? You see my face now? So there, no video, yeah. Okay, now you can see me. Okay, but you won't see me for longer. So because the idea of this webinar is to show you a very straightforward machine learning technique that we are developing in Bioversity-CIAT Alliance. And then what we're going to do is taking about like 10 or 15 minutes in trying to catch up everything. So to be sure that we are all on the same page. And then we are going to 3 examples using, the first example is using experimental citizen science data from Nicaragua with beans. The other example is trying to combine some crazy data I compiled from wheat in India. And the other example is more a social economic aspect on social investments in a survey that was did online. Okay, so now I will turn off my camera and we are going to the presentation. Do you see the presentation? Yeah?
It says Gosset's not available.
Not available?
For 362.
362?
Yes, Gosset is not available for our version 362.
Oh, this is odd. Okay, we are we are having problems here, but I will go to this right now. Let's go to the slides. Sorry, guys. Okay, so first is the idea here is to show like a very straightforward machine learning technique. The content is some concepts to be in the same page. I'm going to show you our workflow here in now what we do in Bioversity in the analysis. Then we are going to a case study with beans, another one with bread wheat, and another one with social impact investments and questions and answer. And also question and answer can be every time here. I will ask Kai to keep track on the chat. So in case someone asks. First thing, what is machine learning? So it depends on who you will ask, but my concept of machine learning is that you are teaching a computer how to do some task. No, it's like training a baby, basically. So here's machine learning is the scientific study of algorithms and statistical models that computer systems use to perform. So basically, machine learning is what people from the last like 15 years ago couldn't done because they don't have computers. Now we can do this because we have better computers. So there are different types of machine learning. The first one is supervised learning, and the other one is unsupervised. What we are going to see here is in that webinar is the supervised learning with regression. And among of these regressions, we can see one kind that's called decision tree. So that's the kind of model that we are going to working on today. So what is a decision tree? No, decision trees comes from this approach. It's called recursive partitioning trees, or rpart. It's a machine learning method for classification. It classifies things, and it creates a decision tree that strives to classify members of a population. So there is like a derivation of like a variant of this rpart that is called model-based recursive partitioning that's what we are going to do. So for example, here we see an example now. So it's an example about what's your attitudes in terms of investments. It's an example from this Saylay's paper. So it's just to show that it creates this tree that you can help you in taking decisions, no? And how it works, how a decision tree is built. First thing, what we did is it fits a model. Basically, a decision tree it fits in a GLM model, in a linear model. So what it does, it fits a model with the full data, all the data you include in that model. And then what this is going to do, it will look for instabilities in that data. So for example, imagine that you have you are trying to predict the probability of teenager to smoke or not based on how his friends smoke, no? So for example, the cutting point in this will be my friend smoke, my friend doesn't smoke. So when the model looks for the data and he tries to look for instability to see if the people that has friends that smoke has a different attitudes, and the other one that doesn't smoke has another attitude. So he looks for instabilities in that parameters. Then, if there is significant instability, so it split the data in the covariant that has the stronger effect. In that case, is my friend smoke or not. And then it does this recursively, like until it fulfills the entire instability across the data to create that tree. So basically it's this, and the trees have some problems, like there are some problems in the trees because you cannot have any cut-off point, no? That's why we also call this branching the tree. You have to cut off some branches to reduce noise and make it better to create predictions. So one way to reduce the noises in these trees, in rpart trees, is doing cross-validation. So I think everybody here have heard about, and I'm just showing what is cross-validation, is taking a set of a data and trying to train the model with this, like you're teaching the model with this, and then you compare if the model learned something with a separate set of data that's called test. And the cross-validation does this recursively across k folds as you can create, no? So depends on which kind of fold you want. And forward selection is also something of, imagine that you have, for example, in my case, I sometimes I have like 100 variables or predictors of a model. So in that case, it's very complicated to know which variable is the one that explains better your model, no? So to do this, what we decided to do is create a forward, not create, but apply a forward selection, which basically computes a model without covariates, and then is adding models as it finds the model with the best prediction or the best explanation. And there is different ways to do this, like you can use AIC or deviance or whatever goodness of fit. And we also saw that deviance is the best approach also, because in AIC includes the degrees of freedom of a model. And when you do cross-validation, you basically lose these degrees of freedom. No? So we use a deviance. And another concept that I will bring, so we covered everything about machine learning. Another concept that I will bring is just quickly is what is citizen science. It's when you have people that were not trained to do this task, but they can do. Like it's we had in the last webinar, we had a nice example of citizen science. When you asked people about how long they take to their routes, how long was the transition from each route. So this is an example of citizen science. So basically, this is people contributing to a bigger task. And triadic comparison of technology is an approach that we develop in Bioversity with the aim to help farmers in test new varieties or new technologies in their farms. So imagine that you have, I don't know, 10 varieties of beans, and you want you want to test this across 800 farms in some country. So you cannot provide the 10 varieties to a farmer because it doesn't, the farmers don't have time to evaluate everything. So what we do is basically randomize these varieties across farmers, and we distribute these in a random way, just labeling the varieties as A, B, C, and we develop when we give to them a package so they can test this in their farms. So each farmer receive a randomized technology, and then they send to us the information. So basically, the randomization is based on the randomized control trials. So it's very controlled. It's not a crazy randomization, but it's controlled also to make sure that we are dividing packages across geographic locations. So we will not only try one package in one region and forgetting another region that is also important. So the package also consider distribution, geographic distribution, the randomization. And how we apply these methods, how we apply machine learning, forward selection, tricot, and citizen science. In our case, we use this workflow where in A, for example, you see that a lot of people contribute to a project. And the way we combine all this data, because everyone produced one data now, so the way we combine this data is converting all the data that we get into rankings. I will explain this later in the next parts of this section, and then we convert this into rankings. And then you see here in B, what we do is also adding, for example, in the case of crops, we add the location and the planting dates. We combine this with weather data and also DNA data sometimes when we have it. So in C, what we do is, since we produce, I don't know, 100 variables that we cannot explain, cannot be not so easy to explain a model with 100 variables, what we do is run recursively, and how the time it takes to run cross-validation forward trees. We have a forward selection, and inside this forward selection, we have cross-validations. In part D, what we can have is that in that part, the farmers get a feedback on what they evaluated and how it was performed across the sites. But since we do this also for the good of science and to forward to make it better, so we keep on this track, and in A we take a stable rpart tree, and we use this for further analysis, trying to make predictions and also geographic extrapolation. So basically, for example, after E, for example, after part E, what we get is this, we can continue this analysis, for example, and we have the tree, and then we can make a geospatial extrapolation with seasonal forecasts, for example. So imagine that you have the forecast for the next season on the beans production in Nicaragua, and then based on this forecast, we can create this not so nice. It's visually, the map's not so beautiful, but at least it represents the geography of this location. So what this map shows here is the recommendations for varieties in a target season in Nicaragua. So for example, the ones that has the orange color, these regions for that season, we recommend Inta Sequia and Inta Centro Sur, and it goes for the other colors. Okay. And then we developed these packages to help with this workflow. Package Placket Loose is the one that builds the entire model. It's an application implementation of the Placket and Loose models, and we put this all together to build this. The packet GoSet is it's one that helps us in combine Placket Loose with forward selection and cross validation. We named this package after William Gossett, which is more known by T student or student. So he was the guy. He was basically pioneering experimental agriculture, but he couldn't use his surname because he has an agreement with Guinness. So he decided to use this the name T student. No, that's why he's most common known by student than Gossett. And we have CleanUp tools that helps you to download the data, your data from the CleanUp platform. CleanUp is the platform we upload all the data from the citizen science. And Climate Trends is the package that helps you to collect the climatic variables. So now let's go to the hands-on part, no? First of all, we are going to evaluate common beans in Nicaragua with the tricot method. So in that case, we have 842 data points from farmers across Nicaragua. And we evaluated 10 varieties of beans, plus the local, the variety that they grow there. We did this in 5 seasons in Nicaragua. And the temperature data is derived from MODIS, MOID 11A1. And why we did this? We did this because it comes from a larger study, a global study, and we wanted data that can be representative across globally, no? So it was possible to use like local data, but we decided to use global data to make it comparable across locations. And also the precipitation data come from chips. Next, we are going to evaluate the bread wheat data in India. So I compiled 255 data points with 18 varieties, 4 seasons, and the grain yield data. So it comes from station data. It's a more convenient way data from most of people here, no? And the other one is a social application. So let's move to our script. I sent to you the script, no? Did you saw? So for example, here, if you for the ones that didn't saw it, if you go here to that link, you just need to copy and paste into your R section. I will just wait you like 1 minute for you to do this. Huh? I will go. What? It's not available for? 3.63. It's the same error, no?
Same one. Yeah, GoSet.
Oh, if you don't have this package, it's a huge problem. I will go to check this error. Are you having this error also? Can you type the error so people know? Because here in the room, we have 2 people with this problem. They say that they can't install this GoSet package. So I will take a look on that. Warning, install our package is not available for R363. Huh?
I just get the warning.
It's a warning.
Just the warning.
It's installed?
Yeah, okay. But did you change this to this link up there? Because there's a new install package. Okay, this so that install into this one.
Ah. I think Steven Steven is are you hearing me? Do you hear me? Steven is
Steven is here.
No, but it's Steven. No, the people there.
Yeah.
But I think. But I think.
There is a slight physical.
Yeah, of course. Yeah, of course. Steven, no, because I saw you have two problems, Steven. First problem is you don't have R2s, and the second one you need to do this. What Daniel is saying, you have to use install GitHub, because it's not there in CRAN, no. So try to use this.
The thing that's highlighted at the top.
Yes, the one that I just sent, this one. Install GitHub, and then it has the path for the it has the path for the repository, and also you can. I put this upgrade never, because I don't really know why DevTools want us to upgrade. So here, for example, this is the first one. So I try to do everything online, so you don't need to have data locally. So we are trying to fetch everything from. Did you manage? Okay. So now we just run these lines, no? Line 11 to line 21. Line 21 has some functions that I built because one package that we used to use, they were removed from CRAN 2 days ago, and then yes, and then I had to copy all the functions they had and use this thing here. And then we will explore a bit the data, no? So DT is our data, line 29. Everybody follow me? Yeah? Okay. So for example, here we see that the data is basically this, no? It has here, for example, it has the packages in this line. Each line is an observation. So imagine that each line is a farmer that provided data, no? And then we have the variety for that farmer received. So for example, you see that it changes across farmers. And also we have that farmers, they reported which one was the best and which one was the worst in that case, no, in their case. So for example, best and worst in this row here. And also they reported which one was the best and worst for compared to the local variety. And also we have the longitude, latitude from that area, the planting dates, season, which season, the growing degree days, and these variables. I reduced the number of variables because I know which one will be taken by the forward selection. So to prevent like taking so many time here, I took only this for example, no? Like to build the example. And then, for example, we can plot here. I made this function. We can plot this here and see how it was distributed. Now, so for example, here is the distribution of these points in Nicaragua. So here was how they were distributed, and here we have the 10 varieties which were evaluated. So in the package GoSet, we have a function that's called rank tricot. It was built specifically for this kind of data sets. So line 46. So here we just need to introduce the data set in this argument, and then we have to just say which columns it should look for the items that are the varieties, and each column it should look for the input that is like the evaluation, no? So when we do this, it converts our data into a what we call a Placket-Loose tree. Oh, Placket-Loose rankings. So for example, if you look here, you are going to see that now it returns like the name of variety and a sign like a positive or big, how can I say this? Larger, a larger sign. So what it means here is that interferoso, it's better than PM2 Don Ray, which is better than Inta-Rojo. So this applies for everything here. And that's why the way Placket Luz prints. But if we transform this into a matrix, I will do this very quickly here. We are going to see that what it do, it basically transforming this in permutations, no? So for example, here we have the varieties, and each row is an observation. So for example, when we have one, this means that interferoso is like best. Interferoso is best here, so I made a mistake when I said to you. So, and Inta-Rojo is the worst because it's 3, and Don Ray is the second one. So all the zeros are the values that the farmers didn't evaluate, like the varieties that didn't evaluate. So here we have a partial rank. So, but how this partial ranks looks like? Because you can say, yeah, but not all farmers evaluated. So how do you connect all these dots, the missing dots? So Placket Luz does this for us. So here we can check the network. So for example, here in this network, we can see that all varieties are connected across the experiment. So it is a kind of social network, no? So we can see that all varieties are connected here, and all of them has arrows, both side arrows, no? So this means that they are connected from both sides. So this means that the randomization worked well, basically.
Is it actually by construction a complete graph?
The graph it's made by iGraph randomly, the way he did. No, so if I run,
there is no guarantee that this is a complete graph, right? It happens to be complete.
Yes.
Seems, but it might not be.
Yeah, it might not be. And for example, to check how the network it's done, Placket Luz has a function that's called connectivity, and I just need to run this, and I can see the connectivity. So when the numbers are all equal, which means that they belong to the same network. So sometimes, for example, when you combine data from different sources, they cannot be so well connected, so it will create a new network. And this is very, very difficult to put all together later when you analyze it. So
you are aware you are breaking the schema data barrier every now and then with this code.
Yeah.
Well, you turn data into attribute names, etc. That's what you're doing, right?
Yeah.
Any theoretical computer scientist would shiver.
Yeah.
Say that.
Yeah.
It's fine, go ahead, but
Yeah.
I'll just tell you that theoretical computer scientists would go like, what's happening here?
Yeah, that's something. For example, if you read the Placket Luz paper that was published 3 weeks ago,
Yeah.
the main author, she says something about that. Okay. So she also recognized this, yeah. And she says that some implementations are needed for big data analysis. Sure. Yes. So then we can see, for example, there is some functions that we can look for the dominance, how dominant these varieties were across the experiment. So for example, here we see that Inta Fuerte Sequia was the one that wants most because it has the highest values and it wants across everyone, no? And this one, ILS is 0 whatever, it has one of the lowest dominance across the experiment here. And also we can also look for the favorability, how preferred these things were across the experiment. And here we see that Inta Fuerte Sequia was also the one that was preferred, and Inta Precoz was the one that was least preferred. Now, for example, we can fit a simple Placket Luz model in line 76. Everybody's following me?
We're trying.
Yeah, I accidentally ran the whole script, so yeah, I'm with you.
Okay, but the all script should work well. I will just, what I'm going to do is just explaining what is like say, going outside this, no? So you don't so Placket-Luz basically is built on the what we call worth parameters. So it computes the probability of each item beating the other one. So it's basically a value that sums to 1, and the highest has the highest probability. So here we just fit a simple model, and in this simple model, this is a implementation of a linear model, no? So here, for example, we see that Untitled-CIAT is the one that has the highest probability of beating all the others. Just a quick remark on this. In this Untitled-CIAT, it was a variety that was released to endure a draw, no? So it's a variety that farmers are looking for in that region. And in that specific moment, we had a very huge problem with El Nino. So basically also the climate and the what happened in that region supported drove farmers to like this variety instead of the others.
What's the demand?
Yeah, and then we can plot this just to take a quick look on how the variance and covariance are distributed. So we can see the name here because it's too big, but this is the Untitled-CIAT. And then, but we want to add also to that rank, we want to add the comparison of the local variety. So we are going to build a new rank, and that is the same thing, but here we are going to add the data frame. So instead of adding the index for the data, we need to add the data frame, which has the comparison with the local variety. No, this. And if we do this, it will create on line 88, line 88 until line 93. So if we do this, line 95, we can create a new network. And this new network has the local variety as center of the network. Of course, because the local variety is evaluated by everybody. All the farmers evaluated this variety compared to the others. Okay? And then I will not run this. It's again, but the local variety was preferred. This has some implications, sociological, psychological implication, because sometimes farmers prefer what they already have in that region. So they are very skeptical of new things. So yes, so when you ask them if do you prefer the new technology or what they already have, they will say, yeah, what I already have is nice, but what you have is also nice, but I prefer what I already have. So, huh?
One question is the rank is affected by the number of people who rank varieties towards each other, or
yeah, the ranking is affected by the number, but it's.
But if it's the most common one, does it happen that often?
No, it's not. It's not like this. No, and also there are. No, this is not the case. And then, for example, now we have to build some another thing that's the writers of this Placket-Luz package says it's called the grouped rankings. It's basically a rank, but it's grouped because it can be indexed to covariates. So you can add explanatory variables, because for now we only did was running this without covariates. No, so now we want to see how these varieties behave when they are exposed to different climates, for example. So we can build the group rankings with this function. It's called a ranking tricot, but we just need to add this argument. It's called group true. So basically, group rankings has the same behavior as the rankings, but the only thing you see that they have this index here. These index are the rows names in the data set. And this is the explanatory variables we are going to use. No, the latitude, longitude, the planting date, season, the year, and all the climatic variables. I will not explain, but for example, this is GGD, is the growing degree days. The mean NT is the minimum night temperature during the during the planting date until the end of flowering season, flowering period. Maximum night temperature is also from planting date until the end of flowering. MLDS is the maximum length of dry spell, so the number of days without rain. And the other one is maximum length of wet spell, and the other one is the maximum 5-day temperature, so it's a heavy day temperature, rainfall. All these indices, they comes from an experiment that CIMIT did, and it has a nice publication of over 30 years of experiments in Mexico. So we combine the explanatory variables here, no? So here we have the combination. So we have the rankings with the explanatory variables. And as you see, it said here, too many variables. Let's create a model that best explains these rankings. So what we want in our approach is to create a simple model, no? The simple, the best, for example, at least here. So we don't want so complicated stuff that we cannot explain later. Enough with the placket loose. And then we built this forward selection. What forward selection does is trying to create a cross-validation. Do you remember the cross-validation? No? So it runs a cross-validation across season. So what for climate matters, no? So what we want here is to try to predict which variable represents better the across seasonal climate. So how is the ability of that variable can be translated across different seasons, not only across folds, no, in the cross validation. So the folds, what we call the bins or the folds in that cross validation will be the season. And the number of folds will be the number of seasons, no? So we see here 5. And we have to say to the function which package we want to export. The package is placket loose, and which goodness of fit we are going to do. So we decided that deviance is the best here because we sometimes lose the degrees of freedom. So it's better to stick to the deviance. And the number of cores. So the forward selection is a function that runs in parallel. So here I put 2 cores. I hope that it's best, but in my case, for example, we'll put 2 cores. And then means is an argument for the packet loose model. This means that how many observations I want in each tree. When I create the tree, how many observations I want in each node, on each block in that tree. So in our case, we think that 30% of the data is enough to not create a thing that goes so deep into the model. And we decided to do the Bonferroni correction. You can look for example, if you want to know which parameter it is, you just need to type this question, placket loose, and we say to you all parameters.
Is there multiple testing issue here?
Yes. And we put the alpha as 0.0. We want a very strict model. And pseudo rankings is something that placket loose creates. That is a way to deal with the missing data, like the data that you don't have in the partial ranks. So we saw that pseudo rank is of 1.5. It's enough to improve the connectivity. Even the connectivity here is being okay, but it's nice to make an improvement. It doesn't affect the model. It just is used to make creation of the connectivity and prevent an error caused by the matrix package, sparse matrix. A problem is called show mod. It's a problem when the matrix doesn't fit well when you're trying to combine everything. So here I just put the system data just to see how long it takes. In my computer with 2 cores, it takes 2 minutes to run it. So here we see the function is forward, and what we do is put the variable, no, the G, the rankings, for everything. The function will take care of running the forward selection and add the empty model before running every other variables. We put the data, the seasons, and which is all the parameters here, and we run. So you can run it, and meanwhile you can ask questions or whatever. So it creates some messages, and I will take a look. Do you have some questions? I expect that it takes like 2 minutes to run.
And it'll take 2 minutes to run.
This is any question related for now, or we are good?
It's a relatively small data set. It's pretty resource intensive to do this analysis.
Yeah.
Yeah.
What would be the added value if you compare it to some other approach?
Which other approach?
You do a regression, like model regression. I mean, apart from data, if it's the model, it's gone, but
for example, in that case, this data cannot fit in a GLM model, regular GLM, because we don't have the true value. We just have the rankings. But for example, there is a paper I can send after this. That another colleague wrote a paper, and he compared the GLM with this, and the power, like the information loose, is not that much to create noise in the data, in the results. So for example, now in my computer, this is running in the second step of forward selection. In the first step, it selected the variable maximum night temperature, and then it ran for the second step. And in the second step, it didn't find any variable, so it stopped there. So the only variable that explains the data and is enough to explain the data is maximum night temperature. And what is nice in that approach is because we can create this in an entire pipeline, no? So for example, imagine that we have another experiment in Central America with the same varieties. The only thing we need to do is add this data into this same model and create another model with new information, no? And then it can change. For example, maximum night temperature could not be the next variable, but can be a combination of other variables. Okay. So what we can have here is the goodness of fit, no? So in that case, for example, we have this AIC, we have the deviance, we have the log likelihood, we have the new log likelihood, and we also have some pseudo R-square values. And the candle tau here is 0 because we are using local variety, and it creates a different dimensions in the matrix. So I didn't find a way to compute this. So in that case, when you use the local variety, it returns a candle tau 0. But candle tau, candle tau, it's like it's a correlation. It's like a Pearson correlation, but it's used for rankings. So for example, here in the model, we see, for example, in this function, we can see all the trees that were built. For example, this is all the trees that were built across folds. And this is all the estimates from each fold. For example, we can see here how the performance was across each run in the cross validation. Some folds that doesn't do very well because there are some problems in also explaining the data. So here, for example, we can take which was the formula. So this is the formula, line 195. And then we can run a single placket loose tree because, for example, in other case, what we can do is do an ensemble model of that trees, no, and create a ensemble of everything. But what we're going to do here is create a single tree for the model that we found. And we can have the summary, and now the summary looks different. We have the summary of the placket loose tree. The placket loose trees also allows you to do prediction, so you can use the function predict from R. And what it returns is the worth values, no? So how is the probability of that variety beating the others, and also the coefficients from this. So we have two rows of coefficients because we have two nodes. And this is a way we can see the tree, plot PL3. And here, for example, is the tree. That's the tree. So, for example, when you have maximum night temperature above 18 degrees, this is the probability of varieties being selected. So, for example, Interforte-Sequia. When you have temperatures below 18 degrees, the local variety is the one that has the highest probability of winning, of being selected, and Interforte-Sequia as well. We also have this worst regret, which is a theory from social economics. And it means that when you don't have any information about the data set on the, for example, when you don't have seasonal forecast, what you can do is using this to compute the probability of regretting less. So, for example, imagine that you are investing in a stock chain company, and you don't know which one you want to invest. So you can apply this theory to see which stock chain is the one that you're going to have the least regret if you put your money there. Okay? So, for example, if you don't have any information about the seasonal forecast for the varieties, you can combine this with the risk we can combine the two approaches. So you can use, for example, the win probability, which shows that Interforte-Sequia is the best one and local. And also you can use the worst regret, which says that the variety that has the least regret is the Interforte-Sequia as well, is the least value. So basically, this is what this approach does. This is a very specific approach that we develop in Bioversity, and I will go to show you a approach that can be more generalized to different cases. Just showing, like, do you remember when I show the pipeline? No, the pipeline that we developed, and in that pipeline we have I said that the farmers get the results, no, the feedback from what they evaluated. So basically, they get something like this. This is a project from chocolates. I used people tried some different kinds of chocolates here in Nepal, and then I made this report to show them. This is all completely automated. So, for example, they got a nice explanation on what was and what they evaluated, and also the same plots we checked later, no? The favorability, which one is best in sweetness, which one is best in bitterness. So these kind of things, but this is just an example. But this is basically what the feedback we give, we return to the people that work in this project. Of course, the farmers don't get this full report because they don't need this. No, they only get a 2 pages report, a compact version of this one. Everything okay? Okay, so what we're going to do now is going to a different approach. Imagine that, for example, now in big data and this entire philosophy, we want to compile data from different sources. No, so imagine that you have I don't know, 25 years of experiments in Colombia, and you want to compile everything and evaluate and see, for example, what's the performance of the cassava gene bank in Colombia, for example. So here I brought a very quick example on how to combine data from different sources. We believe, for example, in the paper that you can later check this paper, but in this paper of Placket Plus, we believe that rankings can be sometimes a nice way to combine data, because you don't need to worry about scales in that data. I will show this example now. And then you lose a bit of information, of course, but if you don't have any other option, it's the best way to deal with this. So in that case, we are going to use that script. I will type for you now. Here the script. Okay. So in that script, we are going to evaluate wheat varieties in India. I will pass a bit fast on the Placket Loose stuff because we already covered this. I will just clean my R section. So this is the wheat data. This comes from participatory variable selection, variety selection in India. We're going to use the same functions, the same packages. And this is how the data looks like. We have data from 2,255 points. And this is the data set. So we have the ID, which is the plot from where it was evaluated. We have the varieties here. We have the planting dates, the flowering dates, the number of tillers, and the yield. And we have the year in which it was evaluated. No? So remember that this data comes from different sources. No? So we don't have control on what it was collected, who collected, and the scales that were used to collect it. It was hectares, quintals for hectare, or grams for whatever. This is grain yield, so it's remember this, no? This is just an example to show how we can combine data from different sources. So for example, here is the map showing where these plots were located across India. So basically North India, in the Uttar Pradesh and other regions. I will just show you here in the box plot how the yield data, that's the one that we are going to use, yield data. And this is the box plot for the entire yield data. So do you see that it's completely out? It's completely out of everything, you know. So it's completely lost. But if you look for the data by box plot by project ID, we can see that it's not so bad now. It doesn't look so bad when we divide it by ID. And when we divide it by plots, it's look a bit better. So now we can see what we can expect here is that the problem was in the scales, no, in the units, which some plots are using kilograms per hectare, and the other one are using quintals per hectare. So the units is the problem here. So what we can do, you can shoot me and you can criticize me if I'm. What we can do in that case, for example, is some of things that we are proposing, and I'm doing tests to check if it's correct, like if can be correctly applied, is instead of using the values, the true values from that plots, we convert everything into rankings. So for example, imagine that the variety that has the highest yield in that plot, that variety will be placed as the first one in the ranking. and the variety that has the lowest yield in that plot, it will be ranked as the least variety. So we lose the yield, so we cannot use this data to predict the yield, but at least we can use this data to predict which variety performs better in some locations, or to select genotypes, for example, if you want to select genotypes from breeding programs. So for example, here we have another function that's called rank numeric. So we can just need to add the data, the variety, the yield, and the ID. So it will split the rankings across the IDs. And instead of having the yield, we have the rankings. So this is the rankings for the experiment. And this is how the network looks like. So here the network, it's a bit messy because you remember that this data comes from different sources. So some points of these networks doesn't connect both, like they don't have a both sides connection, but some of them, they just have one side connection. We can also look for the adjacency and also for the connectivity to check if everything is okay and if everything belongs to the same network. Also, the same visualization explanatory analysis just to check the dominance. I will jump to let's jump to the line 97. Line 97 is the one that I use to add the covariates, the explanatory variables, how we can add the temperature and everything. In that case, we are using NASA Power data. I know that NASA Power has a problem in the resolution because it's a 0.5 degrees resolution, so it's very, very poor resolution in terms of. But I use this just because when you don't have local data, when you don't have data on your own computer, if you don't have any way to do this, you can use NASA Power. But I would recommend you to use a better gridded data, like a data with better resolution. You get an error in the temperature, of course, this is expected. The error in the temperature is expected. I will tell you why. And because NASA Power needs, do you remember the map? Here's the map. In the map, it covers a very huge area in India. So when you ask for the data from NASA Power, it needs a resolution of 10 by 10 region, which means like a 0.5 degrees. So it's like it's like 5 degrees region. So it requires a 5-degree regions, and now we are asking data from a region that covers almost 10 degrees. So what I did, and I blocked these lines because it takes a bit of some minutes, and also I thought that would be not nice to have 30 people asking for the same data to NASA Power. So I blocked this. But what I did was I divided the data. So here's in the blocked line, I divided data by longitude. So if the longitude it's lower than 18, so it is a different set of data. And if it's higher than 18, so it goes to another place. And also I divided by years, so it makes the call more effective. So it will call the data by each season, not for the entire period. And then I create an empty matrix, empty data frame, and I will fill in this data frame in this loop as it will be built by the call, by the NASA Power call. But if we run this line 137, we already have this temperature data. And the temperature data when I wrote these indices, I also try to be more to cover other areas, and I added one index that it's called consecutive frost days. Of course, for India, it's not so useful. In that plains in India, frosty days is like it's not so common. So we are going to see an error here. So for example, what I'm going to do now is to look for the distribution of these variables. And then I plot it using ggplot line 148. And here we see the distribution of this, no? So for example, the consecutive frost dates, it's nothing because of course there wasn't frosty days there. But we can see that the day temperature range, which means like how the temperature fluctuates between the day and the night, this is how it appears in the entire data set. In the other variables, no, the maximum day temperature, the tropical nights, and the summer nights, summer days and tropical nights. Tropical nights is when you have nights above 30 degrees Celsius, of course. And then we combine this data, no? And we remove the lines which has the ID, the time span, and the temperature, the tropical nights, and the consecutive frost days. And we built this as ranks. So this is a grouped ranks now. And also this forward selection, it will take a bit of time. It will take like I don't expect it takes so fast. So I also know which variable will be selected in that forward selection. The variable that will be selected is the minimum day temperature and the minimum night temperature. I forgot to tell you that these temperatures is for the planting date to the beginning of flowering. So maybe we are not covering, because I did this for the sake of the webinar, but maybe we are not completely covering the true significance of the temperature variables for the wheat, no? Maybe, for example, the variable that explained better is one that goes to the grain filling or flowering period. But for the sake of the webinar, let's not complicate it. So let's imagine that this was the one that was selected, but to not go to take so much for your computers and time. I will run this, of course. And this is the plot we got from that experiment, from that combination of data, no? We saw, for example, that the minimum day temperature, when the day temperature is below 19 degrees, so that's how the variables behave. When the temperature is higher and the mean temperature is also higher, so that's the behavior. And here is that the behavior when the night is high, when the day is higher but the night is low. So when the day is when we have very warm day but very cold nights. So that's how it behaves. So just let's take a better look on this using this function that calls plot nodes. And plot nodes, what plot nodes does is creates the same nodes here, but with error bars. So for example, this is the node, this is the values for the first node, and the gray line means that is the average between all the probabilities. So the ones that pass these gray lines are supposedly the best varieties in that node. So for example, we see that could be like the candidates. So imagine that we want to select wheat varieties for a breeding program or whatever to the next generation. So this could be like the candidates for a breeding program. And if you look to the other node, this one is the one that wants more. And this is also the other ones. And here the other node also shows 3 candidates for that class of climate variability. So what we do, so to create this more geographically, we can just take, for example, a raster of seasonal forecasts and use the same predictions that we get here from Predict-CIAT. And we can just pass these predictions to a raster with seasonal forecasts. But for now, for example, in my case, if you know everyone, maybe Julian and Steven are the best in creating seasonal forecasts, because I heard from years ago that Julian was working on it, no? In creating seasonal forecasts for Central America. So for now, that's the problem we have now, to actually have the data for the seasonal forecasts. I don't know if I have time for the other example. Do I have time? Jau? Joe? Yes, I have. Okay, I will go very quickly. This is the one, since I saw that the group was a bit diverse, so I tried to do an example that doesn't only cover crops and plants and everything. So this is it's a almost silly example, but this is to show you how we can apply this on social data, for example. So this is just an experiment. I will send to you I will send to you the full rank, because we just have 20 minutes. So this is, oh no, not this. It's wrong. Here, this is the script we are going to use for that part of the exercise, and this is some survey that was done to check what makes you invest on social impact business. No, if you have some money and you want to invest, which of the choices we will prefer to invest your money on? If it's a social impact investment, or do you prefer a corporative investment? So basically, that is it. So we have this data set. This is 865 observations across different countries. So we have the ranking. So people said, for example, for this SIB is social impact business for young, social impact business for health, social impact business for school, SP is a kind of investment, fixed deposit, corporative, and BBC. And this is the age, and if the guy has saving, which is the gender, what is the income of that person, what is the sector the person works, in which region the person lives, and what is the education he lives, and if he's a foreign citizen in that country, if he's a native or foreign in that country that he's living now. So we run everything. We can run everything from line 1 until line 73. And meanwhile, well, you see that, for example, the first variable that was selected was gender. So it means that the explanatory variables that makes the most strong power in the decisions in which we will invest is the gender. And then donation. So if the person made some donation, so it also makes a strong powerful and like a decision in which investment you're going to take. And the other one is region. So we saw that it takes 3 variables for this, and we are going to look the tree that was built. So for example, in that example here, the social example, we see that when you are a man and you never made donations, so you're very likely to invest in a corporative investments. So you don't care so much about social investments. But if you have made donations, this is real data. No, it's not. If you have made investments and you north, you also don't care about impact investments, but you have some likelihood to invest in social impact business for school. If you are from the south, you also have more likelihood to invest in schools, like in social impact investment for schools. The woman that made donations, they prefer to invest in social impact investments for schools as well. But the woman that never made donations and live in the north, they prefer school and health and corporative. So this is nice because it shows this tricot shows you which is the best impact investment for like which is the which target group you have to look for when you want to make people invest in some stock chain. This is also nice, for example, if we are working in agriculture, for example, if you want to check which kind of farmer, which kind of group we have to do like for breeding programs or how can I say it? Extension programs, no? And this is showed in that. I will just show you quickly that also GoSet has a something that's called BT permute. BT permute, it looks for pairwise comparisons between choices. And we have a nice example here from Ethiopia when one of our colleagues, he asked farmers which are the best, which they want for advisory, and what makes they decide which are which advisor they prefer in agriculture. The other thing is that this function, the forward selection, it has also implementations for GLM and GNM models. So if you don't really like, sorry, but I don't trust in these rankings, it will lose power, I prefer to stick to the GLM model as it is. So you can also use it. There is a nice example. If you look for forward, there is an example showing this with the air quality data from R. This is a data set that is R's hairs. So this is a linear model. You can also put which family you want in that model and which kind of model you are running. The call here is for the GNM package, but it's running a GLM function. And let me see. So for example, this is what we had. And the final remarks is the pairwise comparison and the implementation of GLM and GNM. So this is also possible if you don't want to use the placket loose. And yeah, thank you for the Big Data platform for this webinar, and thanks to my university. And this is my Twitter if you want to follow me and or write me on my email. Thank you. Okay, Jau is saying that the seasonal forecast CGIR has a subscription for 6 months seasonal probabilistic. Oh, I didn't pay attention to that. So now I know and I can use it. Thank you, Joe. Khaled, how to compare this way of find out the most significant predictors versus the variable importance in random forest. It's basically the same thing. Random forest uses recursive partitioning trees as well, but the only thing here is that we can convert this as a worth parameters. So it's the logs. When random forest runs, it runs in a log scale, and in placket loose it can be converted to 0 to 1 scale. So that's basically the same thing.
I think CIAT also has a project with seasonal forecast together with the University of Columbia.
Okay.
Diana Carolina Giraldo is leading that. We had a training last year with the Mexican Net Service.
Okay.
Might be worth
checking that. This is our seasonal climate forecast, and I mean we do two things. We have the seasonal climate forecast and the seasonal agroclimatic forecast, and so those are tailored specifically to beans. And we have those on various countries around, something like that.
Okay, so now Steven said that he also has this data set for Central America, so it's nice to know. And
Yeah, and I mean, it depends on the country and it depends on.
yeah, for example, when I was like 2 years ago, I had some talks with Julian and other, I don't remember the other names from CIAT, but we had, the problem was predicting Central America because it has influence for Pacific and also Atlantic coast, so it makes very difficult to Central America. And yeah, so I hope it has improved, but okay. And always this data set, it covers the entire world, or it has for a specific region? I think he didn't catch me. World, okay. But you have to provide the coordinates. Okay, it's nice to know. Yeah, it's nice. Any other question? Any other comment, critics? You can also you can check my all this 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 is in the GitHub now. So everything that I presented here is in the GitHub, and you can also, for example, if you want to take a look how the analyses are done, for example, for this workflow, we have this climb mob analysis, which shows how it goes from analyzing the data to producing the reports I show to you. And the package gdistance that was mentioned in the other webinar is also here. He lives here now. He changed it. We also create a better, nice visual way, and we are calling for help to improve this package. In the other section, we saw that this the package has some problems running very large model because it takes time. This is because the implementation in R, no? So people that knows they are very proficient in C++ are welcome to help us. Anything else? My Twitter again, please. Okay. I don't publish politics. Only agrobiodiversity and R stats, unless I really run into politics, but I prefer not talk about this.
To say anything about Brazilian politics.
No, yeah. If I will talk about Brazilian politics, I will stay all day in Twitter. So I prefer not. Okay, I think this workflow can be also helpful for climate change adaptation atlas project, where we will need to review a range of adaptation options to prioritize. Yes, that is indeed what we aim to. We started this thing thinking about farmers adopting new technologies and testing new technologies. And my way to see this approach, I don't know if Jakob van Etten agree, who is the one that that developed this, but my way to see this approach is most towards selecting varieties and going towards like prioritizing things, no, not trying to go towards, for example, crop modeling, because we cannot cover that, no. This is not a mechanistic model. So yeah. Any other? No? So yeah, thank you so much for coming. I don't know why my speaker is not working. I think when we set up this, I don't know why it's not working. But thank you so much for this webinar. And if you have any question, just write to my email. I will write here. And we can talk about this approach. And Okay. Thank you.